The correct procedure for determining the minimum size of a feeder conductor for a specific overcurrent protective device, or OPT, is to first consult Table 310.16 of the National Electrical Code, or NEC, and then apply any directing factors required by 310.15. B2. Let's consider an example to illustrate this. Suppose you have a 225 amp feeder with 5 current carrying conductors consisting of 3 ungrounded conductors and 2 grounded conductors, provided for nonlinear load harmonics. According to Table 310.16, a number 4/0 THWN conductor is suitable for a 225 amp feeder, assuming you are using the 75 degrees Celsius column. Now let's apply the directing factor from 310.15. B2. Since there are 5 current carrying conductors, we need to apply a directing factor of 80%. This means the conductor's ampacity must be multiplied by 0.80. To find the required ampacity before directing, we can divide the OPT rating by the directing factor. In this case, 225 amps divided by 0.80 equals 281.25 amps. Looking back at Table 310.16, we need to find a conductor that is rated for at least 281.25 amps in the 75 degrees Celsius column. A number 300 kcmil conductor is rated for 285 amps, so it meets this requirement. Therefore, the minimum size conductor required after applying the directing factor is a number 300 kcmil. Now let's discuss the equipment grounding conductor, or EGC. According to 250.122. B. The EGC must be sized based on the size of the ungrounded conductors. If the ungrounded conductors are increased in size for any reason, such as voltage drop or directing, the EGC must also be increased proportionally. In our example, the ungrounded conductors were increased in size from a number 4/0 to a number 300 kcmil due to the directing requirement. Therefore, the EGC must also be sized based on the number 300 kcmil conductor. Referring to Table 250.122, we can determine the minimum size of the EGC. For a number 300 kcmil conductor, the corresponding EGC size is a number 4 copper conductor. Now let's consider an alternative approach where we apply the directing factor to the OPT rating first and then select the conductor size. In this scenario, we multiply the 225 amp OPT rating by 1.25, which is the inverse of the 80% directing factor. This gives us 281.25 amps. We then select a conductor that is rated for at least 281.25 amps. As before, a number 300 kcmil conductor is suitable. However, the critical difference lies in how we size the EGC. If we consider the number 300 kcmil conductor as the minimum size required after applying the directing factor, we might be tempted to size the EGC based on the original 225 amp OPT rating. This would result in a smaller EGC size, which would not comply with 250.122. Therefore, it is crucial to first determine the minimum conductor size from Table 310.16 and then apply the directing factors. This ensures that the EGC is properly sized based on the increased ampacity requirement of the ungrounded conductors. In summary, the correct procedure involves the following steps. Firstly, determine the minimum conductor size from Table 310.16 based on the OPT rating. Secondly, apply any directing factors from 310.15. B2. To the conductor's ampacity. Thirdly, select a conductor size that meets the directed ampacity requirement. Fourthly, size the EGC based on the increased size of the ungrounded conductors as required by 250.122. By following these steps, you can ensure that your feeder conductors and EGC are properly sized and comply with the NEC requirements. Let's delve deeper into the nuances of conductor sizing and EGC requirements according to the National Electrical Code. As we've established, the primary approach involves initially determining the minimum conductor size from Table 310.16, aligning with the overcurrent protection device rating. Subsequently, Any applicable dating factors, as outlined in 310.15 b2 a, are applied. Let's revisit our prior example of a 225 amp feeder circuit comprising 5 current carrying conductors, 3 ungrounded and 2 grounded, serving harmonic mitigation. For table 310.16, a number 4/0 THWN conductor rated for 230 amps at 75 degrees Celsius seemingly suffices. However, the presence of 5 current carrying conductors necessitates ampacity dating. Table 310.15 b2 stipulates an 80% dating factor for 4 to 6 current carrying conductors in a raceway or cable. Applying this dating, the number 4/0 THWN conductors allowable at ampacity diminishes to 184 amps 230 amps multiplied by 0.80. This falls short of the 225 amp load requirement. Consequently, a larger conductor is mandated. Progressing up, table 310.16, a number 250 kc mil THWN conductor rated for 255 amps also proves inadequate. Post-dating 255 amps multiplied by 0.80 equals 204 amps. The subsequent size, a number 300 kc mil THWN conductor rated for 285 amps, yields an acceptable 228 amps after dating 285 amps multiplied by 0.80 equals 228 amps, surpassing the 225 amp requirement. Therefore, a number 300 kc mil THWN conductor emerges as the minimum permissible size, aligning with the initial methodology. Now let's pivot our focus to the equipment grounding conductor, or EG. Section 250.122 of the NEC governs EGC sizing, mandating correlation with the ungrounded conductor's ampacity. Notably, 250.122 b emphasizes that if the ungrounded conductors are increased in size for any reason, the equipment grounding conductor, where installed, shall be increased in size proportionately according to the increase in circular mil area of the ungrounded conductors. In our scenario, the ungrounded conductors escalated from an initial number 4/0 to a number 300 kc mil due to ampacity dating. Consequently, the EGC must commensurately increase. Referencing table 250.122, we discern the minimum EGC size corresponding to the overcurrent protective device protecting the circuit. With the 225 amp overcurrent protected device, table 250.122 dictates a minimum number 4 copper EGC. However, the crucial caveat lies in the increase of the ungrounded conductors. Since the ungrounded conductors were upsized, the EGC must also be upsized proportionately. The number 4/0 conductor has a circular mil area of 211,600 and the number 300 kc mil conductor has a circular mil area of 300,000. The ratio of the new conductor size to the original is 300,000 divided by 211,600, which equals approximately 1.42. Therefore, the EGC must be increased by the same factor. While it's possible to calculate the exact circular mil area required and select an EGC based on that, a more practical approach is to refer back to table 250.122, but to look at the conductor size associated with an overcurrent device that would protect the larger conductor. A number 300 kc mil conductor is typically protected by a 300 amp overcurrent device. Table 250.122 dictates a minimum number 2 copper EGC for a 300 amp overcurrent protective device. Therefore, in this scenario, a number 2 copper EGC would be required. It is essential to understand that the EGC role is to provide a low impedance path for fault current, facilitating the rapid operation of the overcurrent protective device and minimizing potential hazards. Inadequate EGC sizing can impede this function, compromising safety. Now, let's address the alternative approach where the dating factor is applied to the operating before selecting the conductor size. Multiplying the 225 amp op by 1.25, the inverse of the 80% dating factor, yields 281.25 amps. A number 300 kc mil THWN conductor, rated for 285 amps, seemingly suffices. However, this methodology harbors a potential pitfall regarding EGC sizing. The EGC sizing must be based on the increased size of the ungrounded conductors. If the EGC is sized based on the original operating without considering the conductor upsize, it would violate 250.122. To reiterate, the NEC mandates a direct correlation between the ungrounded conductor's ampacity and the EGC capacity. Therefore, the initial methodology adhering to Table 310.16 for conductor sizing and subsequently applying derating factors ensures EGC compliance. Let's explore additional scenarios and nuances related to conductor sizing and equipment grounding conductor requirements to provide a more comprehensive understanding. Consider a situation where you have a 200 amp feeder supplying a continuous load. According to NEC 215.2, A1 feeder conductors supplying continuous load shall have an allowable ampacity not less than 125% of the continuous load. This means that for a 200 amp continuous load, the feeder conductors must have an ampacity of at least 250 amps 200 amps multiplied by 1.25. Referring to Table 310.16, a number 3/0 THWN conductor, rated for 200 amps at 75 degrees Celsius, would not be sufficient. A number 250 kc mil THWN conductor, rated for 255 amps, would meet this requirement. Now let's factor in ambient temperature correction. Suppose the feeder is installed in an area with an ambient temperature of 40 degrees Celsius. Table 310.15. B1 provides correction factors for ambient temperatures other than 30 degrees Celsius. For THWN conductors, the correction factor at 40 degrees Celsius is 0.91. Applying this correction factor to the number 250 kc mil conductor's ampacity, we get 232.5 amps 255 amps multiplied by 0.91. This is less than the required 250 amps for the continuous load. Therefore, we would need to increase the conductor size further. A number 300 kc mil THWN conductor, rated for 285 amps, would have a corrected ampacity of 259.35 amps 285 amps multiplied by 0.91, which meets the requirement. In this scenario, both the continuous load requirement and the ambient temperature correction factor necessitate upsizing the conductor. The EGC must also be sized accordingly, based on the increased size of the ungrounded conductors, as per 250.122. Let's consider another example involving voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. NEC 215.2. D provides recommendations for voltage drop on feeder conductors, suggesting a maximum voltage drop of 3% for power, heating, and lighting loads, or a maximum of 5% for feeders and branch circuits combined. Suppose you have a 480 volt feeder that is 300 feet long, supplying a 150 amp load. The calculated voltage drop using a number 1/0 copper conductor is 4.8%. This exceeds the recommended 3% voltage drop for feeders. To reduce the voltage drop, you would need to increase the conductor size. Using a number 3/0 copper conductor, the voltage drop is reduced to 3.0%, which is within the recommended limit. In this case, the conductor size is determined by the voltage drop requirement rather than the ampacity requirement. Although the number 1/0 conductor has sufficient ampacity for the 150 amp load, it is not adequate due to the excessive voltage drop. The EGC must still be sized based on the increased size of the ungrounded conductors, as per 250.122. It is important to note that these factors, continuous loads, ambient temperature correction, and voltage drop, can all influence the required conductor size. It is crucial to consider all applicable factors and select a conductor size that meets the most stringent requirement. Moreover, it is important to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and standards. Let's explore the implications of using aluminum conductors versus copper conductors. Aluminum conductors generally have a lower ampacity rating than copper conductors of the same size. This means that for the same load, an aluminum conductor will typically need to be larger than a copper conductor. Table 310.16 provides ampacity ratings for both copper and aluminum conductors. When using aluminum conductors, it is crucial to select a conductor size that meets the ampacity requirements for aluminum. Additionally, aluminum conductors require the use of special connectors and termination methods to prevent corrosion and ensure reliable connections. These connectors are typically marked for use with aluminum conductors. Furthermore, it is important to consider the expansion and contraction properties of aluminum conductors. Aluminum expands and contracts more than copper with changes in temperature. This can lead to loose connections and potential failures if not properly addressed. When installing aluminum conductors, it is important to leave sufficient slack to accommodate thermal expansion and contraction. Let's discuss the impact of conductor insulation type on ampacity. Table 310.16 provides ampacity ratings for different conductor insulation types such as THHN, THWN, and XHHW. Each insulation type has a different temperature rating, which affects its ampacity. Conductors with higher temperature ratings can carry more current than conductors with lower temperature ratings. However, the ampacity of a conductor is also limited by the temperature rating of the terminations and equipment to which it is connected. In EC 110.14, C specifies the temperature limitations for terminations. Terminations are typically rated for 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. The conductor's ampacity must be selected based on the lowest temperature rating of any connected termination or equipment. For example, if a conductor is connected to a breaker with a 75 degrees Celsius termination rating, the conductor's ampacity must be selected from the 75 degrees Celsius column of Table 310.16, even if the conductor itself has a high temperature rating. Let's explore the rules regarding the number of conductors in a raceway or cable. As we discussed earlier, NEC 310.15, B2, requires directing the ampacity of conductors when there are more than 3 current-carrying conductors in a raceway or cable. The directing factors vary depending on the number of conductors. The purpose of this directing is to prevent overheating of the conductors due to the combined heat generated by multiple conductors in close proximity. When calculating the number of current-carrying conductors, grounded conductors are generally not counted unless they carry harmonic currents exceeding 50% of the phase conductor current. Equipment grounding conductors and bonding conductors are also not counted as current-carrying conductors. It is important to accurately determine the number of current-carrying conductors in a raceway or cable to apply the correct directing factors. Let's discuss the rules for conductor protection. NEC 240.4 specifies the requirements for overcurrent protection of conductors. Conductors must be protected against overcurrent in accordance with their ampacity. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the conductor from overheating and potential damage. However, there are some exceptions to this rule. For example, NEC 240.4 D allows for the next higher standard overcurrent device rating to be used in certain situations, such as when the conductor's ampacity does not correspond to a standard overcurrent device rating. However, there are limitations on the size of the overcurrent device that can be used. It is important to consult NEC 240.4 for the specific requirements and exceptions related to conductor protection. Let's delve into the concept of conductor ampacity adjustment factors for conduit fill. When conductors are installed in conduit, the amount of space occupied by the conductors is limited by the conduit fill requirements specified in Chapter 9 of the NEC. The conduit fill requirements are designed to prevent overheating of the conductors due to the restricted airflow within the conduit. When the conduit fill exceeds certain limits, the ampacity of the conductors must be adjusted to account for the reduced heat dissipation. The ampacity adjustment factors for conduit fill are provided in Table 310.15. B3. The adjustment factors vary depending on the percentage of conduit fill. It is important to calculate the conduit fill accurately and apply the appropriate ampacity adjustment factors to ensure that the conductors are not overloaded. Let's explore the requirements for conductor identification. NEC 310.8 specifies the requirements for conductor identification. Conductors must be identified by color coding or other suitable means to indicate their function. Grounded conductors must be identified by a continuous white or gray color. Equipment grounding conductors must be identified by a continuous green color or a green color with one or more yellow stripes. Ungrounded conductors can be any color other than white, gray, or green. The purpose of conductor identification is to prevent accidental connections and ensure proper wiring of electrical systems. It is important to follow the conductor identification requirements carefully to avoid potential hazards. Let's discuss the rules for conductor splicing and termination. NEC 110.14 specifies the requirements for conductor splicing and termination. Conductors must be spliced and terminated in a manner that ensures a reliable and safe connection. Splices and terminations must be made using approved methods and devices. The splicing and termination methods must be suitable for the type and size of conductor being used. It is important to follow the manufacturer's instructions for splicing and terminating conductors to ensure a proper connection. Improper splicing and termination can lead to loose connections, overheating, and potential failures. Let's explore the requirements for conductor support. NEC 314.17 specifies the requirements for conductor support. Conductors must be supported in a manner that prevents them from being subjected to excessive strain or damage. Conductors must be supported at intervals that comply with the requirements of NEC 314.17. The support methods must be suitable for the type and size of conductor being used. It is important to properly support conductors to prevent them from sagging, rubbing against surfaces, or being damaged by physical stress. Let's delve into the specifics of conductor sizing for motors. The National Electrical Code provides specific guidelines for sizing conductors that supply power to motors, accounting for their unique operational characteristics. NEC 430 governs motor circuits, and several factors must be considered when determining the appropriate conductor size. Firstly, the motor's full load current, or FLC, as listed in tables 430.247 through 430.250, is a fundamental parameter. This FLC represents the current the motor draws under normal operating conditions at its rated horsepower and voltage. The conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current, as stipulated in 430.22. This 125% factor accounts for the motor's potential to draw current above its rated FLC during starting and overload conditions. For instance, if a motor has a full load current of 20 amps, the conductor supplying it must have an ampacity of at least 25 amps. 20 amps multiplied by 1.25. Secondly, the type of motor and its duty cycle influence conductor sizing. Motors used for intermittent or varying duty may be subject to different conductor sizing requirements, as detailed in 430.22. E and the associated tables. These tables provide ampacity correction factors based on the motor's duty cycle and operating characteristics. Thirdly, the distance between the motor and the power source affects conductor sizing due to voltage drop. As current flows through a conductor, it experiences a voltage drop, which is proportional to the conductor's length and impedance. Excessive voltage drop can impair the motor's performance, causing it to overheat, run inefficiently, or fail to start. NEC 430.22 allows for increasing the conductor size to compensate for voltage drop, ensuring that the motor receives adequate voltage under load conditions. Fourthly, the number of motors supplied by a single feeder impacts conductor sizing. If multiple motors are supplied by a common feeder, the feeder conductors must have an ampacity sufficient to supply the sum of the full load currents of all the motors, plus an additional allowance for the largest motor's starting current, as outlined in 430.24. The specific calculations for determining the feeder ampacity depend on the number and size of the motors. Fifthly, motor starter and overload protection devices play a role in conductor sizing. The conductors between the motor starter and the motor itself must be sized according to 430.22, while the conductors supplying the motor starter must be sized according to 430.24, taking into account the starter's rating and the motor's characteristics. Sixthly, the ambient temperature and the number of conductors in a raceway or cable affect conductor ampacity. As with general conductor sizing, ambient temperature correction factors and ampacity adjustment factors for conduit fill must be applied to motor circuit conductors, as specified in 310.15. These factors reduce the conductor's allowable ampacity based on the surrounding temperature and the proximity of other conductors. Therefore, to accurately size conductors for motors, it is crucial to consider the motor's full load current, duty cycle, distance from the power source, number of motors on a feeder, starter and overload protection devices, ambient temperature, and conduit fill. By carefully evaluating these factors and applying the relevant NEC provisions, you can ensure that the motor circuit conductors are adequately sized to provide reliable and safe operation. Let's discuss about the equipment grounding conductor sizing for motor circuits. In addition to sizing the motor circuit conductors, it is equally important to properly size the equipment grounding conductor, or EG, for motor circuits. The EGC provides a low impedance path for fault current, facilitating the rapid operation of the overcurrent protective device and minimizing the risk of electric shock. NEC 250.122 governs the sizing of EGC, and specific rules apply to motor circuits. The EGC for a motor circuit must be sized based on the rating of the overcurrent protective device protecting the circuit, as specified in Table 250.122. The size of the EGC is determined by the ampere rating of the circuit breaker or fuses protecting the motor circuit. For example, if a motor circuit is protected by a 30 amp circuit breaker, Table 250.122 requires a minimum number 10 AWG copper EGC. However, there is a crucial exception if the ungrounded conductors are increased in size for any reason, such as voltage drop or ampacity derating. The EGC must also be increased proportionally, as stipulated in 250.122. This provision ensures that the EGC has sufficient capacity to handle fault currents when the ungrounded conductors are larger than the minimum size required by Table 310.16. In practice, this means that if the motor circuit conductors are upsized to compensate for voltage drop, the EGC must also be upsized proportionally. The amount of increase in the EGC size should correspond to the increase in circular mil area of the ungrounded conductors. The EGC must be run with the circuit conductors in the same raceway or cable, as required by 250.130. This ensures that the EGC is in close proximity to the circuit conductors, minimizing impedance and providing an effective path for fault current. Additionally, the EGC must be connected to the motor frame and any other metal enclosures associated with the motor circuit, as specified in 250.118. These connections must be made using approved methods and devices, ensuring a reliable and low impedance connection. It is important to note that the EGC is not intended to carry normal operating current. Its sole purpose is to provide a path for fault current in the event of a ground fault. Therefore, the EGC must be sized to handle the maximum fault current that could occur on the circuit. In summary, to properly size the EGC for motor circuits, you must firstly determine the rating of the overcurrent protective device protecting the motor circuit. Secondly, refer to Table 250.122 to determine the minimum size of the EGC based on the overcurrent device rating. Thirdly, if the unrounded conductors are increased in size for any reason, increase the EGC proportionally, as required by 250.122. Fourthly, ensure that the EGC is run with the circuit conductors in the same raceway or cable. Fifthly, connect the EGC to the motor frame and any other metal enclosures associated with the motor circuit. By following these steps, you can ensure that the EGC is properly sized and installed, providing effective ground fault protection for the motor circuit.